whatever you want to design in your industrial building or industrial shade, it is to be designed like a laterally supported beam. The remaining part of laterally unsupported beam we will start in the next week, because you have to design the footing also, so I want to complete that part first. So we will start with the fourth unit today, that is the column basis, design of column basis. Now the purpose of the column base is mainly to transfer the column load to the foundation. Now, whether it is a steel structure or RC structure, the foundation provided below the column is always a RC foundation. We always construct a reinforced concrete foundation, isolated footing, which its design you have already learned. But now in that design, you learn how the steel from the foundation, some of the steel from the foundation is also inserted into the column, and all that particular part is completely skipped. We design only the concrete pedestal with some minimum reinforcement in the pedestal, and the column, which is normally erected by using the steel sections. The steel sections most widely used are the I sections. Very rarely we go for angle sections and channel section. Either a single I section, or most of the time we go for a built up columns. Okay, all these columns are resting on the concrete foundation. Now, when we want to erect that steel section on the concrete foundation, obviously we cannot simply put the I section on the concrete. How will you connect both these? Okay, so for connecting both these together, we require one more member in between the column and the concrete footing. And that particular member is called as a column base. Okay, so column base is also required to transfer the load coming on the column safely to the concrete. Otherwise, what will happen at a specific location where there is a contact between the column and the concrete foundation, the load cannot be safely transferred to the concrete, or rather, to transfer it uniformly on the concrete foundation will require a huge dimension of the concrete foundation. So to avoid that, and to transfer the load coming from the column to the concrete below uniformly, we require to provide a column base. Okay, that base is normally provided in the form of a plate. Okay, so these are called as the base plates also. So either the name is column base or base plate. Now, as the transfer of load is from the steel column to the steel base plate resting on the concrete block, the base plate requires a larger area to distribute the load on the weaker area of the concrete, because steel is stronger as compared to the concrete, obviously. So the same phenomenon is considered when the concrete block transfer the load to the soil. So how the transfer of load takes place: from column to the base plate, from base plate to the concrete pedestal, and from concrete pedestal to the soil. So as the load successively goes on transferring to the next material, or to the next component of the entire column footing, the area of that component goes on increasing, because we have to uniformly safely transfer the load coming from the entire structure to the soil. Okay, so thus the load is transferred from the column to the base plate, and from the base plate to the concrete block. The plan area requirement of the base plate and the concrete block depends on the bearing strength of the concrete and soil respectively. That is, the load coming from column is transferred to the base plate. So what is the bearing strength of base plate? That is important. Now from base plate to the concrete, the load is transferred. So what is the bearing strength of the concrete? That is also important. So bearing strength of concrete we require to design the base plate, and the bearing strength of soil is required to design the concrete pedestal. Now in your syllabus, we have included the design of base plate only. We are designing the concrete. We are not designing the concrete pedestal. Okay, so because how to design the isolated column footing you have already learned. Only the thing that reinforcement we do not carry into the column. We keep it inside the footing only. That is the only difference. Okay, so today in when you learn the design of column footings, we are actually designing the column bases. Okay, now how the load is acting on a column, that is also important. Now the load on the column is not always subjected to pure axial. or rather, I should say that practically we will never find a column which is subjected to pure axial loading. As the load transferred from or the reaction transferred from beam to the column, it is always transferred with a certain eccentricity. Most of the times the columns are subjected to axial load along with the bending moment due to the eccentricity in the loading. Okay, so which produces either the uniaxial load on the column or biaxial load on the column. Now, because of this bending moment, it becomes very necessary to check what are the maximum stresses developed due to this combined action of axial load and moment. Now, these stresses are normally developed at the base, at the bottom side of the base plate, as well as at the bottom side of the concrete pedestal. And these stresses should be developed, the maximum stresses should be developed in such a fashion that no tension will act on the base plate or the column footing. Okay, there should be a compressive stresses developed at the bottom of the base plate or at the bottom of the concrete block. In such a fashion, we need to decide the dimension of the base plate as well as the concrete footing. Now, if the tension will develop in the base plate or in the concrete pedestal, obviously the column will be subjected to uplift action, and because of the uplift, the column may overturn. If the uplift will be more, the column will overturn. So to avoid that, we have to decide the dimension in such a fashion that the stresses developed below the base plate and even below the concrete pedestal are within the limit, and they should not be a tensile stresses. Okay, they should be compressive stress. Now, in your syllabus, we have not included the column bases which are subjected to movement. We'll consider only the column bases which are subjected to axial force. Now, based on the type of the column bases, there are two major types. I will directly show you the diagrams of these two types. Can you see the diagram, the word file?
Yes, ma'am.
Okay. There are two types of the base plates. One is the slab base and second is the gusseted base. Now, when the load acting on a column is comparatively on a lower side, or even the column is subjected to axial load and movement, the values of this moment and axial load are within a moderate range. In that case, normally we provide the base plates or the slab base. Now, this is how the arrangement of the column and base plate and concrete pedestal is done. This is the I section, which is our steel column. It is resting on a base plate. So this blue color plate is nothing but our base plate, and this base plate is resting on the concrete. Obviously, all these three units we have to connect together. Then and then only the load coming on column will get transferred to the footing and from footing to the soil. Now, how these are connected? The column is normally welded to the plate, along its entire periphery. And if we are not going for the welded connection, then we have to connect through bolting. Now, the bolting directly, how you can just imagine that we cannot connect the column and the base plate through bolting. Where to provide the bolt? So it is done by providing these angles. So to the red colored section, whatever you are observing, it is an angle and it is normally called as a cleat angle, which is connected, which is used to connect the two members. These are called as cleat angle. So how these are connected? See here in this diagram, the cleat angle, one leg is connected to the column and another leg is connected to the base plate. Okay, so either on both the sides of the column, which are connected to the flange of the column, the two cleat angles are provided. So this is the elevation of the column, this is the side view, so the view which is taken from this side, and this is the top view. In the top view, our column and cleat angles will look like this. Now, if we don't want to connect the cleat angles to the flange of the column, then we also connect this cleat angle to the web portion. So this cleat angle will go inside here and it will connect the web to the plate. So in that case, it will look like this. So these cleat angles are connected to the web of the column, and then the second leg will be connected to the base plate. And the base plates are connected to the concrete pedestal below by using the anchor bolts. Okay, these anchor bolts are normally having a larger diameter, normally 20 or more diameters, and the lengths are normally deep, or the lengths provided to these anchor bolts are higher. So these can be inserted deep into the concrete pedestal to have a proper connection between the base plate and the concrete pedestal. Now, if the column is subjected to heavy loads, we need to design these anchor bolts also. And there is a proper designing of the anchor bolt. So we are not considering that design also here. Now in your syllabus, we will focus more on the design of this base plate. Okay, so this is the arrangement, and when the arrangement is like this, that we have provided only the base plate below the column, the arrangement of the footing is called as a slab base. Okay, this is a 3D diagram, and see here you can observe the anchor bolts, how the anchoring of the plates is done to the concrete pedestal. Now, if the load acting on the column is very heavy, and along with the axial load, the moment is also acting, and that moment is also very heavy, then in that case, normally we do not provide the base plate alone. Because obviously, as the load acting on a column goes on increasing, the dimension of this base plate and the dimension of concrete pedestal will go on increasing, because we have to uniformly transfer the load to the footing, to the soil below. Okay, so if the load acting on the column will go on increasing, the dimension required for this base plate will go on increasing. Now, especially dimension means the thickness of the base plate. Okay, so to avoid the increase in the dimension of the base plate, many times additional plates are provided in between the slit angle and column, vertically, and those plates are called as the gusset plate, and hence it gives rise to the second type of the column, that is the gusseted base. Okay, so when the columns are subjected to heavy axial load or heavy movements, instead of going for the slab base only or slab base type of a footing, we go for the gusseted base. So this is the diagram in which you can see that this is the column, and the column is connected to the base plate through the clit angle, which is connected here at the web, and one more plate you can observe here. This plate, it has a certain width at the bottom, and as it goes on to the top, it is tapered. The dimensions of the base plate, the gusset plate, are reduced. This particular plate is called as the gusset plate, and hence the name of the column is gusseted base. This gusset plate is connected to the column at the flanges. It is provided always at the flanges, and then to connect this gusset plate and the column to the base plate, we require this one more clit angle over here. Now this clit angle is also called as a gusset angle, because the purpose of provision of this clit angle is to connect the gusset plate also to the base plate. Okay, so it is also called as a gusset angle, and this angle, whatever you are observing, which is connected to the web of the column and to the base plate, it is called as simply clit angle. Okay, so this is the gusset angle, and then the entire system is connected to the base plate, and this base plate through anchor bolts is connected to the concrete base or concrete pedestal. Okay, so this is how the arrangement is done in case of gusseted base. At certain locations, even though suppose the axial load is acting on a column is not very heavy, but the column is subjected to vibrations, especially in case of the railway stations or in case of the bridges. There we always provide the gusseted base. We do not go for the slab base. Okay, even in the industrial shade also, we normally go for the gusseted base, because the industrial shades are also subjected to vibrations because of the operations of machines. So in case of industrial shade also, we normally go for the gusseted base. Okay, so in your term work, you have a choice whether to design a slab base or whether to design a gusseted base. You have to decide which type of footing I am going to provide to my industrial shade. Normally, if the height of the industrial structure is not much high, and if the gantry girders are not there, like the industrial shed which you are designing right now, you are not considering the gantry girders. So for that, the slab base is normally sufficient. If you have observed the reactions coming on your reactions of your truss, the reaction values are, if it is low, you design simply the slab base. Okay, because we are not considering the moment also on the columns. So we are designing only the columns for the reaction coming from the trusses. And for that column, whatever the load is transferred from, sorry, whatever the reaction is acting on the column, the same load we will consider as the load for base plate also. Okay, because whatever the load is acting on the column, the same is considered for the design of the base plate. So you can design the slab base, and if you feel that no, my column is having a heavy load, maybe say more than 1500 kilonewton, in that case you can design the footing as the gusseted base. Okay, so if the reaction or if the load acting on a column is less than 1500 kilonewton, slab base will be sufficient. Okay, is it clear, guys? This is the slab base and this is the gusseted base. Now we are designing the slab base means what we are doing, we are deciding the dimension of this base plate depending upon what is the load acting on a column and what is the bearing capacity of the column, sorry, the concrete pedestal, and the bearing pressure acting on this base plate. Okay, so deciding the dimension means we have to decide the length and width and the thickness of the base plate. That's it. And in case of the gusseted base, we need to decide, along with this base plate dimension, we need to decide the dimensions of the gusset plate also. And according to this gusset plate dimension, we have to decide the dimension of the angle also, gusset angle. Okay, so these additional steps will be involved in case of gusseted base, design of gusseted base. Now this gusseted base also we will design only for the axial force or only for the compressive stresses which is developed at the bottom of the base plate. We are not considering the tensile stresses here. We are not considering the tensile stresses acting on the base plate. Okay, is it clear? Any doubts in this? Any doubts?
No,
Hello?
ma'am.
Huh. Okay, so we will start today with the design step for slab base. All these I'm going to upload on VOLP. Design of slab base. This is the diagram which shows us the slab base for the column. So the first step here is, I'll simply, we have to calculate the area of the base plate required. Now that area calculation is based on what is the load acting on the column and what is the bearing strength of the concrete, because based on the bearing strength, obviously the pressure will act on the upward pressure will be acting on the base plate at the bottom. Okay, so the area required is calculated based on this formula: column load divided by bearing strength of concrete. Now, bearing strength of concrete or the maximum compressive stresses developed in the concrete, you have learned it in RCC, that is 0.446 FCK. You have learned it in SDD 1, right? While learning the design of RC structure. So the bearing strength of concrete is nothing but the maximum compressive stresses developed in the concrete. That we have to consider here, which is taken as 0.446 FCK. Now, if you consider the IS code and the clauses given in the code, I will simply show you the clauses where, sorry, the page number where all these clauses are given in IS 800. There is one small correction that you have to make. So open page number 46 where clause 7.4 is given, that is the column basis. Okay, this is column basis. Now all the general information and the requirements, everything are given here. I just want to bring to your notice the correction. uh, I'm just reading the second paragraph here. The nominal bearing pressure between the base plate and the support below may be determined on the basis of linearly varying distribution of pressure. The maximum bearing pressure should not exceed the bearing strength equal to 0.6 FCK, where FCK is the smaller of characteristic cube strength of concrete or bending material. So it is giving us the bearing strength of the concrete, which it is written as 0.6 FCK, which is a typo mistake, and it should be 0.446 FCK. Okay, because you already know that how we obtain that 0.446 value, you have already derived it in last semester. So this is the correction in the IS 800, that this value should be 0.446 FCK instead of zero point 0.6 FCK. Okay, now afterwards, after this, you can just go on reading all this information, and related to gusseted base, slab base, the general information is given here, and the thickness formula for the slab base is given over here, and some of the effective area diagrams are given here. But when we consider the calculations based on this effective area, the calculations becomes complicated, because we need to find out the effective area of the base plate as per this hatched region. Okay, and this area calculation is normally complicated, so I don't go by this method. I always consider a full base plate for the calculation, full area of the base plate. Okay, so now let us see the design steps. Okay, so once we calculate the area of the base plate required, we need to calculate the dimensions. Now dimensions will be the L and B. Now if you consider the diagram here, the base plate dimensions are normally higher than the dimension of the column. Okay, dimension of the column means what is the width of the flange and what is the depth of the total eye section, that decides the dimension, overall outer dimension of the column. So we do not provide the base plate having the exact dimension of this BF and total D of the column, but it is normally little higher. Now to decide that little higher value, we consider that there is a certain projection of this base plate beyond the face of the column. And that projection is normally considered equal along both the faces of the column. So if this is the flange of the column, so and this base plate have a certain projection beyond the flange of the column. Similarly, on another side also, there is a little projection of the base plate beyond the face of the column. So this projection on both these sides is considered equal. Okay, so we assume that the equal projection of base plate from face of column. Now these projections are either considered as A and B if you are considering the values different. That is, the projection of the column along the length is something different, and along the width of the base plate is something different. In that case, we consider it A and B, or if it is provided same, we can consider it C. Hmm? Instead of considering A, B, it is considered as C. But if you consider the steps given in IS 800, I will just go to the same page again. See here, they have clearly mentioned over here regarding the projection. I will just read that clause. When only the effective area of the base plate is used, C square, that value is to be used. Now here, instead of considering the full area, if we are considering the effective area, in that case these projections are to be considered equal, and that value is to be considered as a C. Okay, now I don't make this calculation complicated by considering C and effective area. I consider only the projection here, C here, larger and smaller projection respectively of the slab base beyond the rectangle circumscribing the column A and B, larger and smaller. Instead of that, I assume it equal. Okay, so the designs design become easy when we consider the two values equal. Okay, so assume equal projection of base plate from face of column, that is A is equal to B. Now area of the base plate, as it is rectangular, it will be L into B, length into width. Now length of the base plate is calculated by using this formula. This is not actually any formula which we need to mug up. It is simply a calculation based on the geometry. H is the overall depth of the column. So if this is the length, this is the length of the base plate, this is the h value. H means the total depth of the column plus the projection on both the sides. Now the projection of both sides is considered as A. So this is h plus 2A. Similarly, the width of the base plate will be the width of the flange of the column, that is BF, plus the projection on both the sides. So this is BF plus B on this side, B on this side. So it will be BF plus 2B. So either you consider B or A, because we have considered both equal. Okay, so I have written initially as A and B. If somebody wants to assume these projections different, assume these projections are not equal, then we have to consider AB separately. But if you consider these projections different, not equal, then again your calculation part will become little complicated. Okay, so it is better to assume the equal projection. So the length of the base plate will be h plus 2a and width of the base plate will be bf plus 2b, where h is the overall depth of the column and bf is the flange width of the column. Now equating this area, whatever we have calculated, required area, to this expression, and here in this expression putting the value of length and width of the base plate in terms of this HB and HBF and A, we will find out the A value. A is nothing but the projection of the plate beyond the face of the column. And this projection can be provided maximum equal to 100 mm. It should not be, sorry, this dimension is different. It should be less than or equal to 100 mm. Okay. So once we calculate the A, the length of the base plate, we can easily calculate h plus 2a, and the width of the base plate also can be calculated bf plus 2b. So here the dimensions length and width of the base plate we have calculated. Now the third dimension is, that is finding the thickness of the base plate. So for finding the thickness of the base plate, this formula is given, which is present in IS 800. Okay, so I will go to IS 800 now. IS 800 gives this formula. See the slab base. Columns with slab base need not be provided with gussets, but sufficient fastening shall be provided to retain the part securely in place and to resist all movements and forces, other than direct compression, including those arising during transit, uploading, and erection. The minimum thickness Ts of rectangular slab bases supporting columns under axial compression shall be Ts equal to under root 2.5 W into bracket A square minus 0.3 B square bracket complete into gamma MO divided by Fy. And this thickness of the base plate should be greater than or equal to the thickness of the flange. Okay, thickness of the base plate should be equal to or should be greater than Tf, that is the thickness of the flange. Suppose your Ts value calculated is coming less than Tf value, Ts, this value, Ts value is coming less than Tf, then whatever is the thickness of the flange of the column, that you have to provide as the thickness of the base plate. Okay. Now let us see the expression here, the equation. W is the uniform pressure from below the slab base or base plate on the slab base under the factored load axial compression. I repeat, uniform pressure from below on the slab base under the factored load axial compression. It means if you consider this diagram here again for slab base, this base plate will be subjected to uniform pressure at the bottom. And that uniform pressure is only because of the axial compression. That uniform pressure is calculated as W, small w. And that W is given as C. Pressure W is equal to load acting on a column divided by area of the base plate. It is very simple. Load upon area, it will give me stress. The same concept here. Okay. So the upward pressure acting on the base plate is equal to load upon area of the base plate. With this, we calculate the W. A, B we have assumed equal, and that we have already calculated here in the second step. So we put these values of A, B. Gamma M0 Fy is already known to us. So we'll putting this all these values, we calculate the thickness of the slab base, Ts, and it should be Tf, okay, thickness of the flange of the column. So that's it. This is the design. We decide the find out the dimension of the base plate, its length, width, and thickness. And normally, if the loads are lesser, we normally provide the nominal 4 bolts. These are called as anchor bolts of 20 mm diameter at each corner of base plate with 30 mm end distance. So with 30 mm end distance on this side, 30 mm end distance on this side, we provide one anchor bolt here. The diameter is nominally considered as 20 mm. So 20 mm nominal anchor bolts are provided at each corner of the base plate. That's it. This ends the design of the base plate. Okay, so this is very easy design of base plate. We are simply finding the dimensions based on the load acting on a column and what is the bearing capacity of the concrete below the base plate. Is it clear to everybody? Any doubts related to this?
Yeah.
Okay, so I will immediately start one problem that is also a solved example I'm showing over here. It is already I have typed here, and I'm going to explain you that because it is very simple. We have to simply decide the dimension of the base plate. So the calculations are not much involved. I have already typed it here. Okay. So what is the data given? Let us see here. Zoom it a little bit more. Design a slab base for a column ISHB 300 at 618 Newton per meter, subjected to an factored axial compressive load of 1200 kilonewton for the following conditions. Load is transferred to the base plate by direct bearing of column flanges. It means the column flanges are connected to the base plate directly. Directly means normally it is a direct bearing. Huh? That is the entire load from the column is passed to the base. Second case is load is transferred to the base plate by welded connection. The column end and the base plate are not machined for bearing. The base rests on concrete pedestal of grade M20. Okay, so the grade of the concrete is required because otherwise how will you calculate 0.446 FCK value? So that is given. So the bearing pressure acting on a base plate depends upon the grade of the concrete. Okay, so let us design the base plate first. So the grade of the steel is assumed here as Fe410. See, it is not mentioned at all here in problem statement. So when it is not given, you have to take the grade of the steel as Fe410. Okay, and for this Fe410, the Fu value is 410 and Fy value is 250 megapascal. M20 grade of concrete, the bearing strength of concrete is calculated here 0.446 FCK or 0.45 FCK. It is taken as FCK is taken here as 20, so we get this value as 9 Newton per mm square. Partial safety factors gamma M0, gamma MW. This will be required for design of welded connection. So these values are written from IS 800. And we also write down certain properties of the column section, which is given as ISHB 300 at 618 Newton per meter, because these values we will require for the calculation of the dimensions of the base plate. So thickness of the flange TF is 10.6 mm, thickness of the web is TW 9.4 mm, depth of the section D is equal to 300 mm, width of the flange BF equal to 250 mm. So all these properties you can find out from the steel table for the given section. Now, the first step we have to find out the required area of the slab base. So A is equal to load upon bearing pressure. So load P divided by 0.446 FCK. So through this, we find out the required area as 1,33,333.3 mm square. That is the required area. Okay. Now let us provide the base plate, obviously a rectangular base plate with the sides of the base plate as L and B. L and B. Why rectangular? Because your column overall dimension, if you consider, these are not square dimension. Okay, if you consider here, sorry, the dimensions of the column D and BF, it is not equal. So obviously we need to provide the rectangular base plate over here. So the sides of the base plate we assume as L and B. and the overhang, that is the projection of the base plate beyond the column flanges, we assume as A and B. And we consider that projection equal. So we have considered A is equal to B. So area of the base plate will be, as I've explained, the length of the base plate will be D plus 2A. That is the depth of the column plus the projection on both the sides, multiplied by the width of the flange of the column plus the projection of the base plate on both the sides. So D plus 2A into B plus 2B, that we equate to the area required. D value we already know, BF is also known, A and B are equal. So by putting the terms in terms of A, we calculate A value as 45.5 mm. I will round it off to the higher value, which is 50 mm. Okay, so maximum value of A you can consider, you can assume up to 100 mm. Okay, do not provide the projection beyond 100 mm. Otherwise, what will happen? These projections beyond the face of the column will start behaving like a cantilever beam. Okay, and then it will create, or whatever the um, pressure acting below the base plate, it will try to uplift the base plate upward. Okay, because of the excessive cantilever portion. So do not provide the projections of the base plate beyond the face more than 100 mm. Okay. Now based on this A value, we can simply put the value of A here in this expression to find out the length of the base plate and width of the base plate. So length of the base plate is coming as 400 mm and width is coming as 350 mm. Okay, now we have to find out the thickness of the plate. So to find out the thickness, we have to find out the bearing pressure of the concrete, which is calculated as load upon area of the base plate. So load is acting as 1200 kilonewton converted into Newton divided by area of the base plate is 400 by 350. This value is 8.57 and this value should be less than the compressive strength or the bearing strength of the concrete. Otherwise, what will happen? See, the bearing capacity of a concrete is 9 Newton per mm square, and we have provided suppose you have provided the dimension of the base plate so small that the bearing pressure acting on a concrete or below the base plate is higher than the bearing strength of the concrete. Obviously, your concrete will start crushing. Okay, because your concrete has not it is not having a capacity to bear that much bearing pressure or that much compressive stresses. Okay, so see this, that's why we need to provide. If you don't provide this particular base plate below the column footing, this check will not get satisfied. Check means normally the, see, you have already learned the punching effect of the load acting on the footing in case while learning you the RCC design of RC footing. Okay, so that punching action should be avoided on the concrete pedestal. Otherwise, what will happen? Concrete will crush. So that's why we require a some mediator in the form of a base plate which will transfer the load coming from the column to the footing with a larger area safely uniformly on the concrete. Okay, so this is the another check, that the bearing pressure of the concrete, actually this is the bearing pressure on the base plate, it should be less than the bearing strength of the concrete. If not, if this check is not getting satisfied, it means you need to increase the dimension of the base plate, increase the dimension of the base plate, if this check is not satisfied. Then the next, to find out the thickness of the slab base. So by using the formula which is given in the code 2.5 W, W is this value we have already calculated, bearing pressure, into bracket A square minus 0.3 B square into gamma MO divided by Fy. This entire term is under root. So this, by putting all these values here, we get the thickness of the slab base as 12.84 mm, and this value is coming greater than TF. So this is also satisfied. Now as it is 12.84, we have to round it off to the higher value, and that rounding should be to the even value. Normally the base plates are available with a even number of thickness. Even number thickness, whatever we consider, it is of 6 4 mm, 6 mm, 8 mm, 10, 12, 14, 16, like that. So hence we do not round it off to the 13 mm value. Hence, provide a base plate 400 by 350 by 14 in size. This is how we decided, or we considered the, or we designed the dimension of the base plate. Okay, now this base plate is to be connected to the concrete by providing a nominal 4 anchor bolts. Now, before going to the further anchoring bolts, etc., two conditions are given. What is the condition? That the load, first condition is that the load is transferred to the base plate by direct bearing. This implies that the column end and the base plate have been machined for perfect bearing. Also, there is no bending moment, therefore, the connection of the column with the base plate need not be designed. If the perfect bearing is not there, whatever the connection is there, that is to be is to be required to be designed. Okay, now however, to keep the column in position, two cleat angles of nominal size 55 by 55 by 8 see here, the cleat angle size should be also the minimum one. Minimum is actually 50 by 50 by 6, but it is normally increased little bit to 55 by 55 by 8 may be provided for connecting the column flange with the base plate. Okay, so a proper bearing between the two members, that is the column and the end plate, is there, then we don't need to design the connection separately. We simply provide two nominal size cleat angles which are connected to the column flanges and base plate. Okay, and when connected means these two cleat angles are to be connected by providing two bolts, minimum two bolts to the flange and minimum two bolts to the base plate. Second case is that the column end and base plate have not been machined for perfect bearing. Therefore, the load from the column will be transferred to the base plate through the welded connection. Here too, we have to consider the connection design here. Now, how the welding is provided? If I will go back to the diagram here, this diagram, the entire along the entire periphery of this column, the weld is provided. When we consider the connection between column and base plate, either we provide the cleat angle, or we completely weld the entire periphery of the column to the base plate. Okay, so that length is calculated over here. I want the length first now for finding the length of the weld. So that length is calculated over here. So what is the periphery now? How to calculate that periphery? See this BF, BF into 2, and thickness here we are not providing the weld. Here we are not providing the weld. Now this BF includes the this part also. If I will go to the top of this diagram, this is the entire BF, but we do not provide the weld at this junction. So this TW value here, see, I repeat, the weld is provided at this edge and then here also at this edge. Okay, so weld is provided here and then it goes here. So on the opposite side, I can show it is provided here also. So that's why these values are calculated as 2 times 250, that is the width BF of the flange, plus 2 into 250. Are you getting this value? So this exterior side of the flange and interior side of the flange. Similarly, other flange, exterior side and interior side. Now in the interior part, this web of the column is present, where that much thickness of the web we have to deduct, because there how will you provide the weld, na? So this is deducted here. 2 into 250 plus 2 into 250 minus thickness of the web 9.4. Is it clear? हे समजलं एवढं?
Yes, ma'am.
Similarly, now
आणि ते
coming,
पण twice deduct करायला पाहिजे.
sorry,
आणि thickness of the web पण twice deduct करायला पाहिजे ना.
ट्वाइस कसा येईल? या बाजूला नाहीये ना, इथं एक्सटिरियर साइडला कुठं काय, इथं फुल लेंथ पकडतोय आपण.
मॅम पण इंटेरियर साईडला पण आपण दोन्ही साईडचे एरिया इंटेरियर कन्सिडर केलेत ना, मग ते दोन्ही साईडला पण जॉईंट आहेतच ना वेबचे.
अच्छा, म्हणजे
तिथे एक
इकडचं
हा
आणि
आणि
इकडचं
इकडच्या
म्हणतोय.
बाजूला.
हा,
हा
ओके
हो.
ओके. So it is 2 into 250 minus 9.4. Okay, 2 into 9.4. It should be 2 into 9.4. Correct. Okay, so I will make this correction and then upload the corrected copy. Then similarly, plus, while considering the web. Now the weld is provided on this side as well as on the another side of the web. So 2 into depth. Now we have considered directly the depth, and from that I have subtracted the TF, thickness of the flange from both the sides. Okay, so 2 into 300 minus 2 into TF, that is 10.6. This is I am getting the depth of the or the length of the weld along the web of the column. Okay, so the total length for the welding around the column is coming as 1539 mm. Okay, now we will provide, let us provide 8 mm fillet weld. Now the same steps whatever we decide for selecting the minimum size of the weld, maximum size of the weld, same thing is done here. It is considered over here that it is 8 mm size of the weld. Now when you consider this diagram again, there are total 12 number of end returns. What is that end return? See, here is a corner. This is a corner. And from flange to this side, when I move, there is one end return. Similarly, another edge. Second end return. Similarly, on the another side, two end returns. On another flange, again 2, 2. On the another side, 2, 2. And at the joint of web and flange, there is one end return. So, in short, every corner of the column which are rounded. Every corner of the column which are rounded. So how many corners are there? 1, 2, 3, 4 on one flange, 4 on the another flange, so total 8. 2 on one joint of web and flange, and 2 on another joint of web and flange. So 4 plus 4 plus 4, 12 end returns are there. Okay, so all end returns. Now when we consider the welding at end returns, there is a clause given in the code. So let us go to that clause first. So I will open now the design of welded connection and how the weld is provided at end returns is given there. When I want to find out the strength of the weld, I have to consider the effective length of the weld only. So I need to subtract these end return conditions from my total length of the weld. So just go to page number 78. Clause number 10.5.11. End returns. Fillet welds terminating at the ends or sides of parts should be returned continuously around the corners for a distance of not less than twice the size of the weld. Hmm? Twice the size of the weld. So our size of the weld we have assumed here as 8 mm. So 2 into 8 mm, for this much distance the end return is provided unless it is impractical to do so. If it is absolutely not practical, then we don't provide it. But if it is possible, then we provide this end return. This is particularly important on the tension end of parts carrying bending load. So columns, they always subjected to eccentric loading. So columns are always connected by considering this end return concept. Okay, now when I want to find out the strength of the weld, I have to consider the effective length of weld. So I need to subtract this end return from the total length of the uh, weld. Total length we have calculated here by considering the dimension of the column or perimeter of the column. So from that, I will subtract now these end returns. Just now we calculated that there are total 12 corners. Guys, just a moment, I need to
Ma'am,
receive the call. Just a moment, I need to receive the call. Okay, guys, sorry, I needed to take this call because it was by the director, sir. Okay. Um. Okay, we were discussing about the effective length of the well, and I think some student was asking some doubt.
Yes, ma'am.
Huh.
Ma'am, why we are deducting the end returns since because when we are calculating the perimeter, we
Hmm.
aren't considering it in the first case.
No, 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 no. Along the perimeter, when we calculate this total length, now we have considered those edges also, na. See
Ma'am,
at,
but we have
huh.
only considered the distance. We haven't considered the thickness.
Okay, 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 okay. Right. Then end returns are not to be required to subtract here. Hmm. Okay, okay. I will make this correction also. I will make this correction also. So these steps are not required. Fine. I will correct everything and then we will discuss again this in the next lecture, because it is almost 10. I will quickly finish the further steps, because if you remember the design of weld, it is the same step. Only this was the change, but this is not required as we have not calculated the total length. Fine, I will make the corrections and the corrected calculation I will discuss again in the next lecture. Let me finish the further steps first. The throat thickness we calculate as zero point 0.7 times the size of the weld. So it is zero point 0.7 into 8, that is calculated here. And the strength of the weld per mm length is calculated as unit length 1 mm into throat thickness, that will give you the area, into Fu upon root 3 gamma mw, the same formula of the strength of the weld. So if you consider the as code over here, this is the formula, the same one which we have used for the design for the weld. And then by using that we calculate the strength of the weld, and we equate the strength of the weld to the total load acting on a column to find out the length of the weld. Okay, so the required length of the weld is 1131 and we have provided this much. Now actually we have provided this much, 1539 is the provided length, and the required one is this one. So the whatever the concept we have considered, that providing the weld along the perimeter of the column is sufficient, or rather that much, all is required. Many times what is done, the weld is provided only on the exterior side, that is on the exterior side of the flange and on the exterior side of the both the web and exterior side of the second flange also. This interior dimension of the flange along with which we have considered the perimeter, that is avoided sometimes, huh? Along that much length, the length of the weld is not provided. This is why it is not provided based on this calculation. See, even if right now if we consider what is this 250 into 2 minus 9.4, this value, what is this value coming? We'll simply calculate 2 into 250 minus 2 into say 9.4, right? So it is minus 2 into 250 minus 9.4 into 2. It is 481.2. So if I will subtract this value from 1539, my value is coming as 1057 and the required length is 1131. So that is not satisfactory. It means I have to provide the weld all along the periphery of the or perimeter of the column. Okay, this is how these calculations are done. So we calculate the length first and then we check whether the required length of the weld is sufficient or not, depending upon the calculated length. Is it clear, guys? So these three steps I need to remove because it is not included over here. That is correct. Is it clear?
मॅम
Hmm?
जर रिक्वायर्ड लेंथ जर खूपच कमी आली तर त्यावेळी आतल्या साईडला वेल्डिंग करायचं नाही काय?
हा, आतल्या बाजूला फ्लांजच्या आतल्या बाजूला नाही करायचं वेल्डिंग, फक्त बाहेरच्या बाजूला करायचं. पण फ्लांज आणि वेब दोन्हीला कंपल्सरी करायचं.
ओके मॅम.
नाहीतर अजून खूप कमी आली लेंथ आणि मी फक्त फ्लांजला देतो आणि वेबला करत नाही असं नाही चालत. फ्लांज आणि वेबला दोन्हीला करायचं. कमी असेल तर फ्लॅनच्या आतल्या साईडला नाही द्यायचं बस.
ओके मॅम.
Ma'am,
येस.
while calculating LA, we
Huh?
are deducting the thickness of the flange 2 times, but it should actually be deducted 4 times, na?
No, 4 times. Why?
Ma'am, because when we weld the web on both the sides, then each side we are considering twice.
This is, yes, this is 2 times 300 na, so this is 300 and this is 300 2 times.
Yes, ma'am, but we have to subtract the thickness of the flange 2 times because on each side the two sides the flanges are there.
So we have subtracted 2 times here. 2 into 10.6.
No, that should be 4 into 10.6.
Okay, from other side also you have considered.
Yes, ma'am. Yes, ma'am.
Right. Okay. So from that right. The other side I completely forgot here also while considering the web, and here also while considering the flange. Fine, I will make the
मॅम हे
correction.
कळालंच नाही आता.
Huh?
ती कोणतं कन्सिडर करते हे कळालं नाही आता.
मला ऐकू नाही येतंय, तुझा आवाज ब्रेक होतोय.
मॅम आत्ताच त्यांनी 4 टाइम्स सांगितलं ना, ते त्यांनी कुठले 4 घेतले हे कळालं नाही मला.
हे बघ, ह्या साइडचं थिकनेस आणि तसंच इकडचा पण थिकनेस ना. आता हे एक फ्लॅंज आणि 2 फ्लॅंज म्हणून हे 2 into 10.6 झालं, बरोबर. आणि तसंच इकडच्या बाजूला पण येणार.
पण आपण ऑलरेडी एजेस कन्सिडर केलेलेच नाहीयेत ना.
नाही
ते
एजेस,
minus का
हो
करायचं?
ना, एजेस कन्सिडर केले नाहीत म्हणून तर मायनस करतोय ना थिकनेस. इथे एजेसचा प्रश्न नाहीये, इथं थिकनेस पकडतोय आपण. हे बघ, फक्त वेबची डेप्थ हवी आहे मला दोन्ही बाजूला. कॅल्क्युलेट कर.
ओके, हा या फेसला 2 मायनस होणार, तिकडे पण 2. ठीक आहे.
इथं जसं गडबड झाली ना, 9.42 नाही पकडला, तसंच इथं पण गडबड झाली की हे 10.6 2 नाही पकडले. ओके गाईज, अगेन देर इज अ फोन कॉल. जस्ट गिव्ह मी 2 minutes. Okay guys, now any doubts in this? This corrected copy
Ma'am.
I will upload on the VOLP.
Ma'am, while considering L effective, why aren't we considering the ages?
If you consider the ages, this length will again increase, right? You just
Yes,
consider that. And how much is the required one?
Okay, so it will become uneconomical and unnecessary weld.
Yes, unnecessarily we are providing the weld. So, and see, practically also, just to provide a weld for a thickness of 10 mm and 9 mm, it becomes a tedious job for the labor also. So these thickness portion we deduct and we consider the longer edges only. Obviously, if this required value will increase, we need to consider that also.
Okay, ma'am.
Okay, all right. So is it clear to everybody? The design of slab base?
Yes, ma'am.
Now next lecture we will start with the design of gusseted base. That is in Monday's lecture. I will explain you the design of gusseted base. Now in design of gusseted base, along with the dimension of the slab base, whatever the steps right now we have discussed for the deciding dimension of slab base, the same are used over there to decide the dimension of slab base. Along with that, we have to decide the dimension of the gusset plate also and the cleat angle or gusset angle. So that is the additional part will be there. So we will discuss it on Monday. Okay. So we will stop here and I will give you the